Recording on.
Cool. Okay. Morning, everyone. So last week we discussed about a couple of graph problems, and today also, like, we are going to discuss one more graph problem. Okay. So last week we discussed about like initially we discussed about BFS, DFS of the graphs and finding the cycle. And the next one is ease path exists between two nodes. So we also discussed about you know writing a method that will return either true or false, right? If there is a path between two nodes, it returns true. If not, then it returns false. And the next one is given a directed graph. We are going to discuss this one today. Given a directed graph, or an unweighted, directed and unweighted graph, I will explain you what is this. And if you given a directed graph, find the shortest path between two nodes using BFS. So how to find a shortest path, right? Graph says like you can reach from one point to another point in multiple ways, right? So this is we need to find the shortest path, even though you have multiple ways, multiple paths. So what path is the shortest between two nodes? So that is the problem. It's somewhere in I think in the graphs books. If you I think it will be in the coding, cracking the coding interview or some other. Definitely, it will be well-known problem. So let's dive into the problem. Um, Karanya, you understood the last week problem, right? So, this any questions on this one? No, right?
Wish. Yeah, I
So,
understood clearly.
so there are last week we discussed two ways. One is using hash set, and other one is like basically if path exists or not, right?
One was
In
using the
the
state
first,
of a node.
what's that? Yeah,
The other one is using the state of the node, and one is using the hash map.
exactly. Yeah, either we can use this node of the state node state variable to find to navigate, or we can use the hash set. So these are the two ways to figure out. Now let's see how to find the shortest path. Okay, so here it is just returning true false. It's not giving any path, right? So what from where you I know we started from here and we ended here, but what nodes you visited, right? We are not
Yes.
printing, we are not we are storing those nodes. If you look at here, we are storing in hash table, we are storing in a queue. Of course, if we are storing in a queue, and we are dequeuing from the queue. So by the end of this loop, um, you know we don't have those elements in the queue. So we are storing in the hash table. But the problem here is we are storing in the hash table. We are storing all the adjacent nodes in the hash table, right? See, you started with a node and you are storing all the adjacent nodes. If they are not part of it, we are storing it. But what we need to store is the exact path that you want to take between two nodes. Okay. So here we are storing every node of this particular adjacent nodes.
Mm.
So, now let's think differently. How can we store the path? And also, how can we find the shortest path? Okay. Let's take this particular graph. Let me do one thing. Just give me a minute. I'm going to put it in another screen, and I will draw the graph here. Okay, inking slate. Okay, now let's take this one. So we have nodes like this. Um, okay, E is here, and D, F, C, and B, and G, and A. Okay. So now here is the different. Of course, we have this one. We have this one. Okay, this is a graph. Okay, and let's assume like this is a bidirectional graph. That means you can go from E to D and D to E. You can go from A to C and C to A. Okay, are you following so far?
Yes, yes, yes.
Yeah. So here, completely bidirectional. You can start from anywhere, and you can reach to other nodes freely. Now we need to find the shortest path. Okay. So let's say we want to find a path between A and E. Okay. Let's see. We want the shortest path between A and F. Let's take F. Okay. So how many paths exist between A and F out of out
A,
of this? First of all,
A, C, B, and F. A, C, D, and
A,
F.
B, A, A,
C, D,
C,
D, D, and F.
D, exactly. Yeah.
A,
And
G, and
A, G, F.
F. Yes.
Right.
Yes,
So of
yes.
course we also have other paths like A, C, D, E, F. That is very longest one. We also have A, C, D,
E, F.
E,
Yes,
F.
yes.
Right. you can you can have all the paths all top to the top, and then you can come back to the F. That is also there, but what is the shortest here?
A, G, F.
AGF, right? So now by just looking here you figured out AGF there. So what is the criteria you figured out why it is shortest?
It is
What
unweighted.
criteria?
And there are
It is
small unweighted, and uh, there are not many nodes between A and F, only one. Whereas in other paths,
exactly.
there is two nodes,
Exactly. In this case, two nodes. In this case, two. Even last one, we have three nodes,
three
right?
nodes.
So,
Yeah.
yeah, that is the main difference here is number of nodes you are touching along the path. And so, you can think of other way as if you are touching a node, you are like counting it. Let's say, what is the difference between this and this? What is the difference between difference means like, okay, this is start node, A is start node, F is and the final node, and how many nodes you touched before, okay, or how many hops you are doing. So you can think of this is a starting station and the ending station. Okay, you started at A, and how many times the train was stopped, right? Number of stations, right? So the first one will be 3, right? So C is first station, D, and then F, right?
Yes.
And what is the value for the this one for AGF?
AGF is two.
2, because you started at A, first station is G and second station is F. So it just directly you reached at 2. Now, so so you figured this is the small because you are comparing these two values,
Yes.
right? So which one is smaller? This is smaller. That's why this path is smaller. This is the ideal path. So
Yes.
just imagine this a really big graph, you know, uh, and you are finding a path between two nodes. There is a graph with 50,000 nodes, right?
Mm.
So by just looking at it, you cannot figure out if I draw a graph with 50,000 nodes on the board, you cannot figure out, right? You just need to go with an algorithm, definitely. So this is the algorithm. Basically you are choosing different paths, and every path you are creating this number. You
Suresh,
are
your
basically
video has
counting.
been turned off.
What's that?
Your video is turned off to save bandwidth. Yeah.
Oh, my
Well,
video turned off. Even you
now
can't see
it is
my screen.
now it is clear.
Interesting, interesting. Yeah, this never happened before, right? So can you
Yeah.
see now?
Yeah, I can see.
Okay. So here, what we are doing is basically, so you can think of this other way around. So every time you are going from one station to another station, you are incrementing this number, right? So how 3 came here, how 2 came here. So from here to here, okay, you reached one station. That means you are we are I know this, there is no weights here, there is no distance between these two nodes, but we are treating the distance between any two nodes is same, correct?
Yes.
See, the distance between C and D and the G and F, we are treating as same. Even though by looking at the graph, you will see this C and D is really small path, but this line is really big. This line is really big, but we are not considering that kind of distance in this algorithm because we don't have the details. We don't know the input was given. It's a unweighted graph. Unweighted graph means there is no weights for the edges. This is called edges, right? Everything is edges, and this is the nodes. So for every edge or vertex is also another name, I think. For every vertex, there is no weight, right? So in this case, we are considering every edge is same. That means the distance from C to D is equal to just a one, a value one. You can think of as 1 kilometer, or 1 mile, or you can think of as just a value one. Right now, again, G to F is also one. So we are giving just a weight of one to every edge. Okay, that is what we are doing actually. That's how you got the three, right? Isn't it? So now go from a now go from a to a, let's go with this path a c d f. Okay, a to c you counted one, and then c to d you counted another one, and then c to f you counted another one, which is equal to 3, correct?
Yes.
So basically, in the unweighted graph situation, so we are giving a weight of one to every edge, and then we are trying to find the better path. So now this was given like 3. Now if you go with AGF, right? A to G 1 plus G to F 1, which is
One.
2. You already reached your destination,
Yes.
right? So
Yes.
now, since you reach your destination, and this is the ideal path, and that is the main that is the shortest path. That is the shortest path, and at the same time, um, uh, that is ideal path as well. So shortest path, we want the shortest path between two nodes. Okay,
Okay.
so this is unweighted. If they provided the weight, if they provided, let's say, from G to F is really long route, it will take the kilometers is not one. It will be like 5 kilometers, or 10 kilometers, or 15 kilometers. These two nodes or these two stations, then definitely that is not a shortest path.
Yes.
Let's say the other nodes are just 1 kilometer, 1 kilometer. The other one is also 1 kilometer. A, C, D, F is just 3 kilometers. This is 3 kilometers, but this one becomes like 1 plus 15 kilometers, and it becomes 16, total 16. So it is not a shortest. If you are taking this bus or train or anything, definitely you will reach by going the other way. ACDF is better than AGF, even though you will stop only one stop, but it's a long route, right? Because they already given the weights for each edge. But in the unweighted graph, so we are discussing about the graph where there is no weights, there is no value for the edges. So that's why in that situation, the only way is you can think of every edge is same. Every the distance
Weights.
between two nodes or the weight is same. You will assign the same weight. That's why we are assigning number one. So one weight or one value for every, you can think of as a 1 kilometer, or anything. So, or maybe fare. Let's say if it could be ticket fare. Okay. So
Okay.
every from one node to another node is just 1,000 or $1. You can think of as just $1. So it's just better, right? If you go with ACDF, you will charge, it will take $3. But where in case of if you go from AGF, it is just $2. You can think of that weight is either dollar or distance. We are just making a number for equal number for all the nodes, for all the edges, basically. Okay,
Okay.
that way you can find out which is shortest. So now let's how can we write the algorithm? So this is not the this is not the only algorithm. So here we found the path and we need to print the path. This is the complex part here. Okay, you found the path. There is a path from A to F, and please, how can we print that path? We want to print like this: A, G, F. That is our path. So how can we print that? Because if it is small, you can think of this is a small graph and you can simply print it. But if the a graph with 50 nodes, or the
Notes.
80,000 nodes, 50,000 nodes, so how can we print the shortest path? Okay,
Okay.
so that's the main challenge here. So how can we do this? So and I already mentioned, so we are going to use the BFS, right? This is you will start from node. This is a starting node, and BFS always goes with breadth first search, right? They always use which data structure?
Q.
Queue. Yeah, that's it. Blindly we just need to go with the queue, and at the same time, uh, i- so in order to avoid the circles, or in order to avoid, like, we don't want to visit the path again and again, so we just discussed in the last problem, we have to use
Hash.
either the node state or hash set. Yeah, exactly. So because we don't want to go in circles. If you
Mm.
came from A to C, C to B, B to F, and again F says, okay, go to G. But G might already be visited from A, so we don't want to go into that circles. So Q never give you that kind of facility. Q is just only put it in the queue, and it won't tell you whether G is already in the queue or not. Right? There is no way. You already added, like, if you start from A, right? You add C and G in the queue, but what happens is when you go all the way to F, F will also tell you, okay, go to G. But you don't want to, put the G two times into the queue, because you will keep on processing, right? That kind of, in order to eliminate that circles, right? Like, in order to eliminate that duplicate calculation, it's not only duplicate, it's never ending. If you don't maintain that hash table, it will be unlimited, like, kind of your algorithm will never stop, right? So that's the problem. So you need to find a way to eliminate the circles, crossing the circle. So that's main purpose of the hash set. Okay,
Okay.
those two are, we definitely need a hash set, we definitely need a queue. Now, um, there is one more thing we need. So basically, uh, okay, let me. I'm just looking at here. Yeah. So just a minute. Distance has depth of the path is okay. So yeah, I'm just looking at the algorithm. So basically, the way to find here is, anyway, you're storing the hash set. You're
Mm.
taking a hash set, and let's do this. Okay, let me try again, and let's go with it's a little complicated. So let's dive into the algorithm. How can we figure out D, F, C? Oh, sorry, this is C and B, and we have G and we have A. Okay, so this is algorithm, right? This is the graph. So now, as I said before, let's take that this starting node is A, and we want to find A to F. Okay, so let's see how can we figure out. It's not E. Let me do this again. Yeah. So we want to start from A. This is our starting node, and we want to reach to F. We want to find the shortest path. Okay. Now, as we discussed before, we want to take two data structures for sure, right? First one is Q. You can see my screen, right? The
No,
whiteboard.
not no. No.
No?
Now I can see. Yeah. No, not now. It
Oh,
is turned off.
oh, is there an internet like network problem for you?
Not for me, but it shows it is for you.
Oh, for
To
me.
save your bandwidth, it turns off the session off. Your video for Suresh has been turned off to save bandwidth, and your bandwidth is connection is inactive for me. Okay, now it is good.
Interest, interesting. You want me to stop sharing and start again? I can try that.
Okay.
Yes, let me try. Okay, sharing some audio. I don't see any warnings or anything here.
Even I don't see anything.
Okay, can you see now?
Yeah, I can see now.
Okay, let's go with it. Let's see. So let me know if you are if you cannot see any progress
Okay, I'll
on the
let.
whiteboard. So here, this is a queue, right? We want to take a queue, and we also need to take a hash set. So
Mm,
until now, so hash set means we want to make sure which node was visited, right?
mm,
So so if you say C is visited and B is visited, like C was visited and you put it in the hash set. So in addition to putting the value of the C, we want to put from where you came, basically. So you want to say like G was visited, but G from where it visited, G was visited from A. Okay.
mm.
So basically, what I'm trying to say is, we want to store the parent node. It's not parent. You can think of this as the node from where you started. Okay.
Okay.
So so the before node, basically the node. Just a minute. I think. Am I going right? Yeah. So next node and node. Yes, that's how we are storing. Yeah. So basically, we want to store something like this. So you want to, let me put it a hash set. You know the hash set, hash table. Let's take the hash table. Hash set has only one variable. You can store only one object, but hash table, I don't know what is in the, I think it's a map. I think it is a map in somewhere in
Yeah,
Java, right? So
yeah, yeah. It's
it's a map. It's a map or hash table in C sharp, whatever it is. You can store two values. You can store a key and a value. Okay.
yes.
This is what we want to take. And this is one data structure. We already took a queue, and the second one is a map data structure. So what is meant by that is, we want to do like this. When you are adding something to the map, let's say this is a list you're adding. So we want to say, hey, G was visited. You started from A, and when you started from A, what happens? You will put all the basically all the children, right? Not children, the adjacent nodes into the queue, right?
Mm,
So when you're adding into the queue, you will also say, okay, if it is part of the queue, let's put it in the hash table. We don't want to put the C or G into the queue again, just for the sake of eliminating duplication. We want to put C and G into the hash table or hash map or map. So now we want to put C, and we want to put G, and we also want to put C into this map. In addition to putting this is a key. Okay. We want to store from where this was visited, from which node the G was visited. Is G visited from F or is G visited from A? What is the value?
A for both.
Exactly. Exactly. So G was visited from A. So now you can have a more context. So you can answer two questions. Is G already processing? Yes, G is already ready for processing. It is part of the queue. G is already ready for processing, and and also okay, from where you came from, like from which node you visited G. Yeah, it was visited from A. Okay, so that is the main advantage of storing. We need to answer two questions. We want to get two inputs, not only just say hey, G processed or not. We want to also know from where that G was visited, which node the G was visited, because the main problem here is we want to print the path. In order to printing the path, you need to know, all the values you visited, all the node names or the nodes you visited. That is the reason we are going to have this. Okay, and the other thing is, let's say you're not just printing the path, you want to print the depth of the path. You can think of as a depth. So in the previous in the previous the diagram, I put all the ones here, right? Let's put one here, one here, one here, one here. So now path from A to F. So there are two paths, as we mentioned before. There are multiple, not only two. Let's take AC. Oh, there is a path here. Sorry, I forgot to draw this. Okay, there is a path here. So now, what is the other path? A, C, D, F is one path, right? And what is the depth of that path? Depth is basically you just need to count how many number of edges, right? Depth is
Yes.
three, correct?
Yes.
So just a one, one, one. So you just need A to C is one, C to D is one, D to F is one. One is you can think of as a kilometers or the distance or the fare, or you can think of as a depth. So this is a depth. You can go from A to F, but you need to, travel, three depth. Okay. Now you want to go with A to F with another path, which is A, G, F. Right. What is the
Uh,
depth here?
Two.
Two, simply two. So we want to store, we want to calculate, or we want to store the depth as well. Okay, that means how can we store the depth? How can we calculate this? So the way we calculate is you're starting from A, you're starting from A, and if you go to G, so we want to take one more step. So we will take, in order to store the depth, we want to take one more hash table. Okay, so now the depth is dynamic because let's say from A to G, okay, you reached from A to G with a depth of 1. Okay, now from G to F. So basically you need to calculate when you are adding F into the table. So what is the depth until now? So what is the depth or the number of nodes you visited now? Basically depth of G plus 1. You following? Let me tell you something like this. A,
Yeah, Suresh, I can get.
can you see the screen or no?
I'm seeing the screen.
Okay. So now A is somewhere in the graph. A is like A and G. There are multiple. There are, you can think of as 1,000 nodes here. Just assume that. Okay. Now you started from A. Okay, you visited all the nodes. Now from G is the 1,000th node. Let's say this is the let's take 100. Don't want to take 1,000. Let's say you visited 99 nodes and this is the 100th node. Okay, that means depth is 100, right? Now you are going to the final node GF, A to F. So now final is F, and what is the depth here? If you start from A, if you are going in this path, you need to reach by 101. Basically, you are just adding one more, right? How three came here? How two came here? Basically, you are adding one plus one plus one. Here one plus one. Correct?
Okay, Suresh. Yeah, I'm getting it now.
With following. So basically, so so from in order to find the depth of a node, in order to find the depth or the fair or the distance of the node, you just need to go back here. Okay, give me the depth of this node, give me the depth of the previous node, and just add one. That way you will figure out how much you want to put here. I put f equal to 2 because the depth of g is 1. That's from where you came, right? And
Mm.
I'm
One to
adding
that.
1 to it. 1 to it. Yeah. So this is all from A. Let's say if I'm starting from E, then if I'm adding F, I should put 1 because from E just only one distance,
Yes.
E to F. So this number will vary. This we are all putting these numbers because it's not a constant. F is not always 2. And
Yes.
if you want to go to the F, it's not always 2 kilometers. If you're starting from A, it is 2. But if you're starting from either D or B or E, it is just 1 kilometer, right? So that's why
Mm.
it's not a constant thing for each node. We are putting in the map, and the map will go away once the algorithm is over. So we are adding one because there is no weight. So we are just adding one for every node.
Okay, this extra map we are creating, we are having it for each path they are visiting, right? For example, we have four
Exactly.
paths from A to F. So now we have taken AGF. So for that path, it is calculating G's weight and F's depth.
Exactly.
And for if
So
we
we will
take ACBF, it will calculate for ACBF for that path only, right?
exactly. It will calculate A, C, D, F, but it won't put F into this table again because it is a hash table. This is also a map. This is also a map. We don't want to put again. So you already reached F. If you're going this path, F will be in the hash table way quicker than if you are going into this path.
Yes.
So in this case, F equal to 3, right? A, C, D, F. It's F equal to 3. So we don't want to store that because it's already there in the hash table. That means you already found a shortest distance to F, you know? So that's why the map is really important here. We don't want to override the value there. We are just putting the values there. So if anybody asks, hey, what is the distance of A to D? Okay, it's 2. A to D is 2, right? So if what is the distance of A to E? It's 3. It's automatically tell you, this table will tell after processing, it will tell you the distance of any node from A because that's the starting node here.
Mm.
Distance of any node, right?
Yes.
Basically distance or depth you can think of as a distance or depth or fair or anything fair, picket fair, anything. So it will tell you, this hash table will tell you the fare from A to every other station. That's what it is.
Okay.
Exactly. And the second, this particular one is basically the first one is map path or hash path. This will tell you the path from where you came, from where, like what is the, I know it is f equal to 2, but what is the path? So you're saying f equal to 2, but tell me those nodes, you know, from A to F.
Mm.
Then this particular hash table, this first hash table will give you that path. Second hash table will give you the fare or a distance or a depth, but the first hash table will give you the path. That is the trickiest part of this whole algorithm. How these two hash tables will tell you all the answers. Q is just for processing. Q is, it won't give you any answers for you. For sure, Q is just for processing the nodes in a breadth first search manner, right? the only the only thing that is the only thing that they are giving you answers is these two hash tables or these two maps First map is will give you the
Okay.
path, and second map will give you the distance. So now we will see how this work. Okay, it is really
Okay.
complicated. Explaining the things is complicated, but once you understood, then it will be easy. So like how we are doing, let's go with an example. Let's go with the example. I'm going to fill the values, then you will be able to understand definitely, because I don't want to show the code unless you understood the full logic, right? So I'm going to erase here. Let's do an exercise kind of thing, one by one. Like kind of we'll run the algorithm and then we put the values. Okay. So now let me remove all this as well, just to make sure it will be clear. Okay. So now one, 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 one. Everything is one. So now let's start from A. Okay. Let's start the normal BFS algorithm from A. What we do in the normal BFS algorithm, do you remember? What we do is, what is the first step in the BFS?
The first step is to uh, enqueue the A.
Exactly. First step is enqueue the A. Yes. Okay. Now, if you look at the other algorithm, I think we are putting in the hash table as well. Not only the queue. Let's look at the algorithm here. So what are we doing? We are immediately adding to the hash table. We are adding to the hash table, and also we are enqueuing into the queue. This is the first step. These two are the first steps, right?
Okay.
We want to make sure we don't want to process the start again, the start node. So we are for the safe side. So we are putting in the queue because queue will process the start node. At the same time, we are putting in the hash table so that it never be processed again. Got it?
Okay. Yeah.
Now we need to do the same thing. So we added to the queue, and we also need to add to the both the hash tables. Here now we are having two hash tables, not one. We need to manage both hash tables. Okay. First hash table will tell you the path. Okay. What is the first hash table is basically, okay, whatever the node you are adding to the queue, that will be the key. Okay, we are going to add a there. And what is the previous node from where you came? No, this
From
is starting
A.
node, right? So
Yeah.
second one is null basically, because basically you just started this node. It's not like if
Okay.
you say G, okay, G, I came from A. Okay, this is basically this is the key, and this is from where you came, how you reached this node. The second value will tell you. The second value is basically the previous node, or the node from where you reached this station, or you reached this node. From A to G, I navigated from A to G. That's what it represents. Okay. So now in this situation, you just landed on A because that's the starting node, right? The algorithm says, hey, find the path from A to F. So you started from A. That's why the value is null. There is no previous node in that situation, right? Now, at the same time, you need to add A here, and you need to tell the cost of it. What is the cost of starting point? Zero, right? You haven't even navigated anywhere, correct?
Okay.
Your part, let's say these are all stations, okay? You belongs to station A, and you are living in that station, and you reached that station without any efforts. It's basically you did not, uh, you know, traveled anywhere. Basically, that's zero. Now,
Okay.
what we are going to do is very straightforward, simple, normal, usual algorithm. What is that? The queue. Basically, we'll have a while loop for queue until the queue is empty. We'll start processing the BFS. Okay, first thing is we
Okay.
will DQ. We will DQ number A, right? We will start processing the A. Processing in the sense what we do. Basically, we will
We'll
grab
check the
all
adjacent.
Adjacent nodes, exactly. We will get all the adjacent nodes. So what are all the adjacent nodes of A? C
C and
and
G.
G, right? Now what we
Yes.
do, the same process. Is C is already in the hash set. If it is not in the hash set, we will put it in the queue and we'll put it in the hash set, hash table,
Okay.
hash set, whatever. Same thing. We will follow the same process. Let's let's see. Is C in the map one? No.
No.
Let's put the C in the in the queue. Is C since you are putting in the queue, immediately we have to add to the both the hash sets. Okay. So add C here, but now here, as I said, this second node represents from where you came from. C came from D or C came from A? From where we came right now? What is the parent node or the what is the node you are iterating basically?
A.
Exactly. A. Cool. CA. We added CA. That means it represents you can reach C from A. Okay. And we also need to add to the second map because we want to make sure
Depth.
we need to calculate the depth as well, right? So C.
Yes.
So the way you calculate the depth here is you just need to calculate the depth of the node, the depth of the A, and plus one. As I
Which
said
is
before, right? As I said before, there are 100 nodes, and here is a 100 node, and this is another next node. What is the depth of this one? Basically, 100 plus 1 is
yeah.
1000. If it is, let's say, if it is 120, just 120 plus 1. That will give
Yes.
you 121, right? So this is the node where you are putting on the hash set. This is the node where you started. This is the node you reach, and you just calculate the fare just by adding 1 to the fare of this node. In order to reach
Okay.
from this station to this station, it is 120 rupees. And in order to reach from this station to this station, what is this? Just 120 plus 1, because we are putting just $1 or 1 rupee for every station to station, right? So that's it. So that's the just basic that's the basic calculation we need to do. So what we need to do is basically, what is the value for C now?
Value of C is 1.
1, because
Of A
the
plus
value of A
1.
is 0. Value of A is 0 plus 1, right?
Yes.
Got it? So now 1. So that means depth, you can reach C from A, and the value, the depth of the distance or the fare is 1. Okay. Now we did that. Now this is done. Okay, let's process the G. Is G in the hash set? It's not there. Is G in any of the hash sets? No. That means G is not processed. This is a very brand new node. So let's put it in the queue, right?
Okay.
Now we are done. We are done with A. So now we processed A. Let's erase A now. Now what we'll do is Q empty?
No, Q is not empty. C is there, so we'll pop C.
Exactly. Let's pop C. Let's take another color, nice color. Let's take blue. So now we pop C there and take the C into the calculation. Now what are all the nodes of C? D,
Nodes of C is D, B, and
B,
A. Since
A.
A is already there, we should
Exactly.
take.
Is already in the maps. We don't consider A.
Yes.
Correct. Now,
Yes.
what is the next? Let's start from the beginning. D. Is D in the hash sets or hash maps? No.
No.
So let's add D. Of course, if you remove, it will come here, right? G comes here, because if you remove C, G come into the next line. Now, is D in the hash set? No. Let's add D into the queue, right? And we need to add D. We also need to add the D into the maps, right?
Okay.
So we need to add D here, D there, and what is the distance? What is the what we are going to add for the second node?
C.
C. Basically, you came from you reach D from C. That is what it tells you. Okay. Now
So now, okay.
is we need to add B also into the here. So
Yes.
what is the depth of B?
Depth of D is C plus 1, which is 2.
Exactly. Basically, DPTH. Depth of C plus 1. That is the formula. So depth of C is 1. So you need to add 1. So that means, okay, is 2. So if you want to go from A to D, it is 2 kilometers. That's what it tells you. It's always A. All these numbers, everything is, represent the distance from the A, because that's our starting point. Okay.
Okay.
D is done. Okay, now B. Is B in the hash set? No. Let's add B to the queue, and let's add B to the hash set, and what will be the value? The same thing, the parent node. All D,
C.
B, the parent node.
C.
You need to add C, right?
C.
And what is the depth of B?
B is also 2. Depth of C
2.
plus 1.
Exactly, 2. Now you're done. A is already in the hash set. You're done. So you're done processing C. Correct?
Mm,
Awesome.
yes. Yes, yes. I've done processing C.
Now let's go to the G. Let's process the G. That's the next element in the queue, right? Of course, every time there is, I forgot to tell you. So um, every time when you are taking the element from the queue, when you are taking element
Mm.
from the queue, we need to check: is this the node do you want? Is this the node you want? Let's say that
Why
say when
not
you
use?
the final node which you want to reach, right? As
Okay.
soon as you reach the final node, you're done. You no need to process the adjacents of F, right? Let's say if you just reached F, you don't need to process the F for adjacents, because you already reached F, right? So every time you're enqueuing, or sorry, dequeuing the element, you need to check whether this is the element that you want, right?
Okay.
When you're in the stage, when you're in the train, you will check, right? Whenever the train stops, you will check whether is this the station I'm going to get down. Correct.
Okay.
So similarly, like let's say you travel for 8 hours, and almost 8 hours your station will come, but you are in the mid of the night, you don't know the station name. What do? You every time train stops, you will check, is this the station I want to get down, right? So
Okay.
we are traveling at night. You can think of as the thing like that. You want to reach from A to F, and every station you are traveling. Is this the station we want to reach? Is this the station that we want to reach? No. That means let's process the next station, right? You want to go to the next node. So G, you just removed G from the queue, and is G equal to F? No, we want to go to F, right? So now let's process G's neighborhoods, neighbor nodes. What are the different nodes? Correct?
G's different nodes is A and F.
A
A
and
is
F,
already
and
in the
A.
map, and
Exactly. A is
F
already in the map.
is the exact destination we have to meet.
Exact destination, but we just checked about D. We just checked about G. We don't want to check every node,
F.
because we haven't
Oh,
we haven't visited we haven't inserted F into any of the maps. Let's don't check
okay.
that time. Just only check when you are dequeuing from the queue.
Okay.
Okay, don't check at this point. If you're checking F, oh, F is something we want. Okay, done. Let's break the loop. Then you don't know there is no way you can find the depth, because you did not
Okay.
add the depth in the table yet. You did not add
Okay.
F into the maps,
Okay.
right? Let's don't check whether the each child is part of the destination node or the end node. Let's simply check whether F is in the maps or not. Is F in any of the maps?
No.
No. And F, though immediately it won't be in the queue as well. So let's add F into the queue, and at the same time let's add F into the hash map. So what is the value for now? Value for F will be,
F
this is
will
the key
be
is F, and what is the value? From where you reached F?
G.
G. Okay, let's put there, and let's put the value for depth of the G, or the distance of the G, distance of F. What is the distance of F?
Distance of F is depth of G plus 1.
Yeah, depth of G is,
1 plus
did I
1, which
add
is
G?
2. No, no, you didn't add G in the
Did I
depth.
forget to add? Wait. I think I forgot to add G in this table, right?
Yes.
Yeah, I think when you process A, right? When you process A, I added. I think I forgot to add. I added only C. I forgot to
Yeah.
add G. So G will also be there. So by this time you reach here, let me
So
put
by the
something
time
like
we
this. So this
complete processing A, both G and C will be there in the maps, both the maps.
exactly. Yeah, I forgot to add into this table. So G will be here with value 1. Just like C, G will also have value 1. So now
Okay.
what is the value of F? The value of G plus 1,
Is 1, which is 2.
which is 2.
2,
Okay.
2.
That's what we do. Okay. That's what we do for value of G. So now you're done with G, right? Because G, you already processed G. A is one node and F is one node. A is not, A is already in the hash set and F is not in the hash set. That's why you added there and you completed adding all the nodes. Now let's process D now. D will into the picture. And what are the values of D? Values of D is so many. E is there, F is there, and C is also there. From D, you can reach all these three, right?
Yes.
Let's put a little bit. I think we need to have a more space here. So let's put somewhere here. So from D, what are the neighboring nodes? E, F, and C. Okay.
Yes.
So now let's process E. Is E in the tables? No, right?
No.
E is not there.
Suresh, your
E is not there.
video is turned off for me.
Again, the sharing turned up.
Yeah.
Should I stop share and share again so that you see? I don't know why this is happening. This is the first time, right? This did not happen
Yeah.
before, right?
Yes.
Just uh, share it again.
Okay.
Can you see now?
Yeah, I can see.
Maybe, yeah, maybe the network bandwidth on your side, because I don't see any problems here. Yeah. So now
Okay.
let's process E. Okay. We will put E here, and what is the value for E? D, right?
Yes.
And D and E is not in the table. What is the value for E? Value for D plus 1. Value
1,
for D is here, plus 1.
2,
2 plus 1 is 3.
which is
Correct?
3. Yes. 2 plus 1 is 3. Okay.
So it will go to the same table. In order to get the value for D, you will go back to the here, and you found this is a 2 plus 1. Okay. Now you completed E, and F is already in the table. No need to do anything. And C is already in the table, right? You don't need to do
Yes.
anything, because we don't want to overwrite F or anything. So it's already there. So now let's process the last but one, which is B. Let's process the B. So now we got the B. What are the values of the B? Which is first one is C and the next one is F,
F.
right?
Yes.
There are two neighbors of B, and let's also DQ from the queue. Okay, so now F is at the front of the queue. F is at the front of the queue, and there is no other nodes. So now you are processing B. So C is already in the table. F is already in the table. So we are good. No need to do anything for B, right? Now you completed processing B. Okay.
Okay.
Now the final node. Now we reached our destination. The final node is F. Okay. Now we will check is this the what we want? Yes, this is what we want to reach. F is the final node. Now what you do? You just stop the loop. You no need to process any other nodes. Let's say F is connected to some other K node, or F connected to another Z node. We don't need to process any of those nodes because you reached your destination, right? You don't
Okay.
care from the destination. Let's say you reached your Mumbai. You don't care what are the other routes from Mumbai. You reached your destination from one route. That's it, right? So
Okay.
now we need to answer the question. Okay, what is the depth of F from A? What is the
Is
depth
2.
of F from A? Simply 2. You can just take the value from the hash table. It is 2. Okay, now you are saying 2. That means you just only with a single hop, with a single station, you reached here, like between the nodes. Of course, two stations including F, right?
Okay.
You now let's get back to that path. Give me the path. How can we answer the path is basically using the first table. So how can we do that is start from
Uh,
F. F is your key, and let's get back to the
G.
value of this key. Yeah, go to this is the key, right? Simply go and look at the value. Okay, G. Now,
G.
okay, what
G.
is
The value
G?
is the value
I
is
think I
A.
think I I think I forgot to add G as well in the
Yes.
middle,
Yes. Yes.
because when you adding C, we need to add G
Yeah.
as well, right? Forgot to do that.
Okay.
So I did the same mistake. I forgot to add G, depth of G
Good.
and the value G when I'm
Got
processing A.
it.
So now basically using the key F, you can find the source
Yes.
of F. The source of F is G, and using
C.
G, you can find the source of G, which is A.
A. D. C. Okay.
So now GFA, it was printed in a reverse order, right? FGA. Basically, F came from G and G
Okay.
came from A. But it should be reverse order. You can just simply print in a reverse order. Nothing matters, right? By using a recursion. Basically, we are using a recursion function to print the path. So I will show you that. So basically, we are asking, hey, you reached Mumbai. Let's say F is Mumbai and G is some other distance. Like, hey, from where you came? I said, oh, I came from this particular
Two.
city. Now you are asking this city, hey, you reached this. From which city you came? I came from A. This is giving you the path in a reverse order. Now if you are printing in a reverse way, you will simply print like this: A to G, G to F, right?
Okay.
So this table will help you. This first table is really important table that will help you to give the path from one node to the another node. Okay,
Okay.
you
Let's
feel it's
see.
complicated? It is, right?
No, 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 Suresh. It is very good.
Yeah.
It is easy.
Yeah, so we need to maintain three data structures. That is important. How to manage those three data structures and what each data structure is doing. This is very critical to understand that whole logic. Okay. Now, if I
Okay.
show you the code, I think you will be able to understand. So, in technically, you should be able to write the code now.
Yeah, I'm doing it.
So, because you know the algorithm. So, but anyway, so let me show you really quick, so I can share the code later. So here is the algorithm here. So it's the same thing. Like we have the exact same node class and everything is same here. Adjacent is same, and here is graph node is also same. The main setup is same. So here is the main. main algorithm is here, display shortest path, right? This is what we want to do, display shortest path. This is the graph node, and this is the starting node, and this is the ending node. This is exactly as I said, as I explained. So we are taking two hash tables. One is hash depth, hash path. Hash depth will give you the depth of each path, and the path will give you the path. Basically, let's have two hash tables, one for keeping the depth of each path as we are going from A to each nodes. Second, to keep track of the previous node for each node, right? This is for the depth, and this
And
is for
this
the path.
path.
Basically, it's just simply in the other way. So I'm saying like this is depth is the first one, and the path is the second one.
Okay.
Okay. So it's a simple same algorithm. Let's navigate starting from A to using BFS. BFS means queue. I took the queue. I put the start node in